Today we're going to look at the second part of the design analysis. We will look at how to use tools to analyze programs' runtime performance. This is a part of the DPC++ tutorial series. We talked about this design flow. We have several stages starting from emulation and then optimization report generation. If we are ready to implement the design on an FPGA, we need to perform compilation to generate FPGA bit streams. And this usually takes a long time. And in the process of generating FPGA bit streams, we can add profiling instrument registers to make it possible to collect performance data at runtime. And that's what we're going to do here. And if we do that, we will be able to execute the binary and then collect performance data at runtime. So how do we compile the FPGA binary for profiling? We'll use Intel FPGA Dynamic Profiler, which use user-added performance counters to collect kernel performance data. And these performance data can be the stall, occupancy, idle, or bandwidth usage. Once the data are collected, at the end of the execution, the data can be viewed in Intel VTune Profiler. At the compilation stage, we need to enable profiling. What we need to do is to add this special flag -x profile to the compiler command. What this command will bring is additional profiling registers, as we show in these yellow boxes. In this example, these profiling registers will be added to the load store units of the design. And the load store operations will be captured in these performance counters. And at the end of the execution of the binary, these counters, the values stored in these counters, will be loaded into a data file, and which can later be retrieved. After we compile the FPGA binary, we can execute the binary using profiling tool. We can perform this execution in two steps. First, we can call this command aocl profile-no-json, followed by the name of your binary executable. In this way, we will execute this FPGA binary and collect the performance data at the end of the execution. And we will execute this binary in a profiling mode. So the performance of this binary will be collected through the performance counters. And these counters will be stored in a file called profile.mon at the end of the execution. And after the execution is complete, we will use this profile.mon, this file, to generate a JSON file so that the VTune profilers can read these files. And to do that, we use aocl profile-no-run profile.mon, which is the file generated from the first command. And that command followed by the name of the executable. So at the end, we will have two files. One is profile.mon, and the other one is profile.json. Both of these two files are needed when we load the results folder to Intel VTune Toolkit. When we load data by importing these data to VTune, we need to check import multiple trace files from directory option when you import the data. Now we're going to show you a demo how to compile for profiling and collect the profiling results. Once you load the data into VTune Profiler, you can see this panel here. On the left side, these are the kernel functions that you loaded. These are the executables that you loaded for analyzing the runtime profiling result. And the main panel here shows a few things. The top portion of this panel shows the important memory operation functions and the loop operations. And then for every operation, it shows the time, the percentage of stall, occupancy, idle time, and activity percentage. Also in this panel, it shows the data transfer in size and also the average bandwidth. So in this example, what we can see here is that overall, this kernel takes about 16 seconds. The number of kernels is just one, and there are about 60% occupancy, and idle time is about 40%, and activity is about 40%. And overall, there are data transfers, and the size of the transfer is about 20 gigabytes. And that is about 1.3 gigabytes per second for the average bandwidth. The bottom portion of the panel shows in more detail along the execution timeline what are the FPGA utilization, FPGA other metrics, for example, global memory bandwidth, occupancy, and how those change according to the time. We can load multiple designs in Profiler, and here we load the runtime profiling data for another executable parallel V2, and we again see the detailed information on the panels here, and we we also see the detailed statistics on the stalls, occupancy, and idle time, activity time. The difference between these two designs is that this V2 version has the loop unrolling, and loop unrolling factor is 2. So by using a loop unrolling factor, we essentially duplicate the resources that we use to load data, and that also slightly increase the total number of bytes loaded from the global memory. But at the same time, because we use 2 ports to load data from the global memory, we essentially increased the bandwidth usage to the global memory. Also, the loop unrolling helped us to coalesce the access to memory so that the contiguous data can be loaded more efficiently. So as a result, the total execution time is now reduced from previous case 16 seconds to now only 6 seconds. So from these two examples, we can see that using VTune Profiler, we can collect a lot of detailed statistics about the execution performance of the design. And from looking at these numbers from the profiling results, you can know more about these individual kernels and their functions. And this will help us to think pinpoint or identify any potential bottlenecks and give us some ideas for optimization. In this particular example, we can see that because the way this kernel is designed, there are a lot of memory accesses to global memory. And in the previous case, there was about 20 gigabytes of access data transfer, and in this case, it's about 57 gigabytes. So that's a lot of data transfers between the FPGA and the global memory. This shows that this matrix multiplication example, the way we design it, it's really a memory bound application. So that motivates us to optimize on the memory access, and we'll show in the next lecture how we can use local memory to drastically reduce the memory accesses to global memory and improve the efficiency of the design.